Welcome to episode 12 of the Cosmic Pie podcast, season number 3.
Yeah.
What do you think, Robert?
About what?
Well, my name is Wayne Barkhouse,
And I'm Robert
and
Moore.
on the right side of me over here, not
Over
politically necessarily,
Over here
just
somewhere,
spatially,
right? Yeah.
We
Over
have-
here somewhere, right?
Robert Moore.
Yeah. Hi, everybody.
You think, how long should we do this for, Robert? How many seasons do you think we'll put in here?
I don't know. Probably as long as people will watch us. I figure as long as we've got a few viewers, we'll keep doing it.
So few like more than
becomes,
2 or something?
or until it becomes not fun.
Until we try to have fun, as
Yes.
you can tell.
As you can tell, hopefully.
Now, do you know what today represents?
April 8th.
And what happened 1 year ago, April the 8th?
Oh, that would have been the solar eclipse, total solar eclipse that was seen pretty much over the entire North American continent.
Yeah, you realize the year's gone by already?
No, I didn't until I saw it on my feed this morning.
In some sense, it seems like a year because it was a long while. A lot of stuff has happened since then.
Right.
In other ways, the way you think about it, it's like it didn't seem that long ago, a few months ago or something.
It popped up on my feed, and I was like, "What? It's been a year?
It's been a year already. So the next good one, and I don't mean like good one as in it's going to happen around here, but the one that I'm kind of putting my eyeballs on is the one in
Australia?
July of 2028 in Australia, Sydney, Australia.
Yeah.
I just gotta, pick berries or something to make the extra money. I wonder what the
Right?
cost of airline tickets will be to Australia from the United States in 2028, given the way the economy seems to be
idea.
going.
I don't know.
Could be like $50,000, so I will not be going there.
Right?
if it's that much.
Wow.
So what I say is predicated on whether I can afford it or not.
that said, it would be a nice trip.
Definitely
As long as
would
you can
be.
overlook the spiders and the crocodiles and the
Well, if you
ants.
stay in the city, your chance of getting exposed to that stuff is minimal. If you go out
Fair.
in the outback, then
Yeah.
you might run into those kind of creepy corals like anywhere else, right?
Like anywhere else.
Like anywhere else.
Yeah. For those that don't know, I mentioned the ants because Australia's got like 3-inch
Can't you eat some of those?
ants called bullpup ants.
Can't
They're
you eat some of
bulldog
those ants? Right? Are they?
I
edible?
don't know. They look mean enough to me that I'm like, I'll just leave you guys alone.
You have to watch the Crocodile Dundee movie and see
Right.
which of those critters you can eat or not. Now, as a disclaimer, which maybe we should have done a few minutes ago, anything that Robert and I say are just our own personal opinions and not necessarily those of anyone else,
Right.
including
Just,
the university, the college, United Nations,
just us.
the Trump administration,
Yeah, just us.
whatever. It's just our personal opinion. We do have a live chat that's running, so if you have any comments or questions that you would like to ask us, then please utilize that feature. And you can comment about anything you like. We have the option to respond or not, don't we?
That's it. And, as long as it's on topic, we generally will.
No nasty things.
Yes. Nasty things will get deleted as fast as we're able.
Yeah, we don't want to get in trouble for nasty things,
Right.
so we have to get rid of those quite rapidly. The other thing I want to mention too is if you don't like watching if you like our Cosmic Pie podcasts on YouTube, you do, but you don't really like it. We also have them available on Spotify. So please check out that venue if that makes you feel better in terms of your viewing pleasure. Now, today we're going to start with some news. The last day, we kind of did other things, right?
Right.
So today we're going to get back to a more traditional sort of
Okay.
viewpoints.
So some news about astronomy and
Yeah.
astrophysics and things that are going on in the world.
Yeah,
there.
last day we did kind of a photo album of the latest images, over the last couple of years, taken by the James Webb Space Telescope. Very beautiful images.
They are.
And in fact, if you did sort of go in depth describing each one and what the relevance is, what it really means, what's cool and interesting about it, you could spend, podcast
a
after
podcast on each one of those images, folks.
Yeah, so we don't want to do that, of course, because then we miss a lot of other stuff happening.
That's why we also say, feel free to ask us questions,
Yeah, so the first thing we want to show today is kind of a leftover from last week, but it is news.
Okay.
It's not like an image taken 3 years ago or anything. And this is the combined image of the Hubble Space Telescope of the planet Neptune, and that's the image taken on the left. And on the right is a combination of the Hubble image again, but laid on top of it, overlaid, is an image taken with the James Webb Space Telescope. And what should capture your attention, hopefully, is the kind of magenta, really soft shade magenta, both near the top left and the bottom right a little bit. And that's actually the aurora.
I was about to ask, is that aurora?
That's aurora on Neptune.
I also noticed that the dark spot is quite bright in this.
Yeah,
So-
that dark spot, the one you're thinking about, the one that was imaged by Voyager when it went by in 1989. That dark spot, as far as I know, has gone away.
Oh, okay.
And then it's, the great red spot on Jupiter is well known for that.
Right.
And since the 1600s, people have reported that. People speculate that spot,
it's
you can
dying
think of it like a
down now.
giant hurricane in some sense, right?
Yeah.
That kind of comes and goes.
Okay.
And there were times when it wasn't really prominent, other times more so. In fact, lately, over the last several decades, as far as I remember hearing about, that spot has actually been shrinking and shrinking and shrinking.
Yeah.
So at some point in the not too distant future, that spot itself may disappear completely. Whether it reconstitute itself again,
Right.
who knows? But we have to kind of wait and see. So it's more, instead of being a permanent feature that lasts for 4.5 billion years since Jupiter formed, it's probably a transitory type of thing
Right.
that lasts
It just-
maybe 1,000 years.
On human scales, it's a long-lasting storm. On
Yeah.
solar system scales, it's
Blink in the
transitory.
eye, a blink in the eye.
But I mention it because that dark spot that Voyager spotted was a convective storm, kind of like the Great Red Spot or a hurricane here on Earth.
But you can certainly see
And
the
there's something clearly there.
Yeah, for sure, and you definitely can see the cloud-like features. And don't forget, the Webb, we're looking at the infrared.
Infrared.
So you're looking
right.
in different layers into the atmosphere. It's not what
Good
you're going to
point.
see by
Good
your
point.
eye.
But
And
getting back to its aurora activity, that's kind of neat in and of itself because that says it's got a pretty strong magnetic field, but we kind of knew that already.
yeah, we knew that from the magnetometer measurements that Voyager 2 made when it passed
Right.
relatively close to Neptune. But Neptune's one of those planets where we definitely got to go back with an orbiter.
Yeah, I guess, yes. Or Uranus, one of the two.
Yeah, I would say
If not
it'd be
both.
nice, both of them, if we could.
Both
if we
would be
could
nice.
Do it.
Yeah.
And stay there for several years doing, complete orbiting the planet, investigating the moon. Neptune also has a ring system, so we could investigate that in more detail. So there's definitely lots and lots that needs to be done.
Right.
Now, the next image kind of goes with this one. So this is a report that came out recently. It was in Nature Astronomy, if I'm not mistaken. And it's some detailed observations that were done over, several year time span, watching the rotation of Uranus itself. So this is through HST image. You can see one of those images on the right.
And again, you can see the aurora.
Right, and you can also see the ring system on Uranus too. Now Uranus is tipped over almost 90 degrees, so the pole kind of points towards us as it
Okay.
orbits the sun. And the big mystery is what caused Uranus to flip over.
Yeah, because that took a lot of energy.
Took a lot of energy, so the speculation is some giant impact very, very early on in the formation of our solar system. And notice both the ring material and the moons orbit the equatorial region of Uranus. So to us, it's like a dartboard,
Yeah.
where the moons go around, face on in the sense of their orbit, the plane of their orbits. It's not edge on like most of the other planets in their moon systems.
Well, it kind of means also that whatever flipped it on its side, the moons were already present because
Well, it would
they
have been
kinda-
afterwards.
Oh, that's right. They would have been
It
afterwards.
would
Yeah.
afterwards.
Yeah. Okay.
So it had to be so early on that it was really before the ring system and the moons got assembled
Right.
to flip it on, or the moons would have been probably,
Would
done-
not have been affected.
Yeah, they would have been done in a different. Well,
So
who
they'd
knows
be-
if there were moons before that and they got destroyed and they went into Uranus,
Right.
become part of, or ejected out of the
ejected.
system completely. So whatever it was a very dynamical, kinetic event that occurred.
Right.
And people try to simulate all of this stuff. And like I said, the latest ideal on this is that some giant impactor, but it's still a complete mystery in some sense. We don't really know per se.
Yep.
The other interesting thing is when you fly by Uranus, it's very difficult to examine its moon system. In fact, Voyager 2, which flew by in January of 1986. The reason why I know those dates, you might wonder, is because in January of 1986, most of the space reporters, the news media, were at JPL in Southern California, just outside of Los Angeles, covering the flyby of Uranus by
Yep.
Voyager 2, and the Challenger explosion happened.
Yes.
And they had to all fly across the country to the East Coast to get to the Kennedy Space Center and to the
find
Johnson
out what
Space Center in
happened.
Houston to investigate all
Yep.
of that. And so that's why I remember these dates.
I remember the space shuttle date. I'd forgotten that it was the Voyager date as well.
Yeah.
And it's because I remember me and my friends hearing about the space shuttle, and we were actually laughing about it, I'm ashamed to say, because space shuttles don't blow up.
Right.
We were in high school, and space shuttles don't blow up.
Yeah. I was actually home that day watching it live on TV
Oh, man.
and saw it happen in real time, in
Yeah.
that sense, right?
And
But I was into the space program. I tried to watch every single launch that I could. And I remember as soon as that had occurred, I knew that was it. It was game
Yeah.
over because I knew the system. Like I said, I was into that stuff, still am. But I knew the system well enough that there's no chance of survival for
Oh,
that
no.
type of event. There's no way.
No.
And you get a lot of reporters that were reporting at the time, and not to blame them, saying, "Oh, we see a parachute. It's probably the astronauts coming." No, it was the nose cone of the solid rocket boosters coming down. Had deployed the parachute because they had
Right.
to blow them up because they were going erratically, right? So you self-destructed those with
Yep.
command from the ground. And like I said, they didn't have parachutes. There was no way that they were coming down on a parachute. It just the system wasn't designed that way at that time anyway.
Yeah.
So anyways, that was that. But the thing is, since it's like a bullseye type of system, you can fly by one moon very closely, but you miss all the other ones,
oh, right, yeah.
right?
Yeah.
Because normally when their orbits are edge onto, you can go by one, then the next one, then the next one. You can time it out, so then you can get most of the moons that you want to in terms of the flyby.
Right.
But you can't do it this way.
Yeah.
So that makes it very difficult to see well the moons of Uranus. So think about this. Let's have an orbiter that would have close encounters of the moons over multiple times, that if you're going to be there for several years. But that orbiter needs to go into an orbit at 90 degrees inclination to the plane of the solar
Which
system.
again takes a
in which
lot
it was
of energy.
launched. So in some sense, I've seen this happen because we've sent spacecraft over the poles of the sun. And what you do to kind of minimize the energy you need initially, that is the rocket that you need,
Yeah.
is you send the spacecraft towards Jupiter on a high inclination orbit, high as possible, and use the gravitational slingshot of Jupiter to go around the polar
Yeah.
area of Jupiter, then back towards the sun to go polar orbit around the sun, and then
And then drop it into
yeah, you can do it that way. But it just takes
That's-
more time.
a lot more time.
But it's a lot less, energetics that you need from
Yeah.
some huge super duper rocket.
And
to
for
launch it.
for reference, the problem is angular momentum. Angular momentum is a conserved quantity, so you've got to expend energy to change how thing is revolving, how it's turning. Anybody who's tried to stop a flywheel knows about that. So since everything is in a plane orbiting the sun, to kick it up out of that plane takes a lot of energy because you've got to bleed off its speed and change its direction.
So you can do it slowly at a time, like you can think of ion propulsion. Mm-hmm. So these are very low specific impulse rocket engines. That means they don't produce a lot of thrust, about as much thrust as you would get if you think of the weight of a piece of paper in your hand.
Right.
But you can have that being applied, that minute acceleration,
For
that
years.
minute force, for thousands and thousands and thousands of hours. And we've
Right.
tested this many times in space. It's nothing new. And that just builds up that change in trajectory eventually to get to where you want to be.
Right.
You
Just
have
takes
to have,
time.
Yeah, you just have to have a lot of patience.
Yep.
That's the only
And
thing.
humans don't tend to have patience.
Unless you're a doctor, then you hope to have,
Then you have lots of patience.
hopefully.
Hopefully.
Now, the next thing that goes on related to our solar system is the presence of a new comet, Robert.
Ooh, another one.
Another one. So
Nice.
this is the one. It was actually detected in SOHO images. So people look at, those are the images taken of the sun, and they have a coronal disk where you block it's essentially the photosphere of the sun plus more.
To cut down the glare.
To cut down the glare so you don't saturate the detectors on board the spacecraft, which is in its own independent orbit around the sun. And that spacecraft is mainly to keep an eye on solar activity, like the coronal mass ejections, the solar flares, these sort of things. And it's been up there for decades.
Yeah. It's was well worth the money to
money
put that one up there.
For sure. And there's kind of a little bit of a cottage industry where amateur astronomers have been looking at the SOHO images, watching comets that get very close to the sun. They're called sun
divers,
or sun grazers.
sun grazers, sun divers.
And they're sometimes those comets are not viewable from Earth very well because they come in towards the sun's direction. So you don't really get to see it because it's in the daytime. And the only reason you can see it is that you can pick it up in the SOHO spacecraft.
Right.
And that usually you pick them up literally just days before they impact the sun. And otherwise you wouldn't know they were there.
You'd never know they were there. But it's been the most successful comet finding mission or set of observations that we've done. So SOHO solar telescope.
Yeah, so an amateur astronomer then, I guess, looking at these images, spotted a new comet. And this comet now is in the sort of the early morning sky, so we can actually see it with the regular telescopes. It was at about, last time I checked, was about 8th magnitude, which is too faint to be seen by the unaided eye.
But binoculars will do it.
Yes, binoculars will see it, or a smaller telescope will see it. But the other thing is that they're predicting, and you got to watch out predictions of comets, that it should brighten to at least 5th magnitude, if not brighter.
Which would put it at high visibility.
Yeah, so if you're in a dark location, you will be able to see the comet.
Nice.
So people are getting some good images. You can see some images taken of the comet here. And if we go to the next slide, you can see another really beautiful image taken of the comet.
Nice tail.
Yeah.
I mean, that's a long tail.
Yeah, very impressive. So hopefully when we think about comets, number one, we don't want them to impact the Earth.
No.
Once we know what kind of trajectory or path they're on and it doesn't intercept the Earth, then the next thing we wish it to happen is come close to the Earth so that it's going to look extremely bright to us. We want a nice bright comet.
Yep.
And we want something, of course, for us that's viewable from the northern hemisphere. Because we've had a few comets that dipped down south.
Yeah, went south.
See. So we'd like to have this one. I'm not sure the exact path. I think this is going to be a much better comet than the last one that kind of stayed by the sun and then dipped south on us.
It's going to be dim, so.
Yeah, we'll see. You never know with these
That's
things.
true.
But
I mean, it could erupt and brighten dramatically.
it could. So we'll kind of keep our fingers crossed on that. Now, the second news item, Robert, do you like to vacuum your house?
I do not. I detest that, to be honest.
So around here, getting rid of dust can be an issue because there are a lot of fields.
Yep.
And in especially early spring or late fall after the harvest, those fields are exposed to the wind more so than if there's vegetables or produce growing on them.
Not to mention all the Canadian wildfires putting smoke in the air.
Yeah, well, I was thinking if there's any wind, and we get a lot of wind around here, it's a flat area, and so that wind can pick up the soil, the topsoil, and next thing you know, it's in your house. If you have your windows open, especially because of the nice spring weather like we're having today. Not to show off, but it's beautiful out there if you haven't been out there lately. And so that dust ends up in your house. But how do you get rid of the dust? Well, dust is a problem not just for your house, but also on the moon. And we've talked about this before, the fact that the Apollo astronauts walking on the moon, one of the things they complained about is the huge amount of dust that sticks to their spacesuit.
Right.
And you couldn't help but bring that into the lunar module because there's no way of sort of getting rid of the dust before you enter your spacecraft. And this becomes a real problem. The dust itself hasn't undergone any type of erosion like you would here on Earth, so it's as sharp as glass.
It's shards of glass, essentially.
Yeah, and that can get inside of different mechanical devices, joints, for example. Gets inside the spacecraft, finds its way inside, electrical panels, you name it.
Now, I do want to mention, when I say it's glass, I mean it's glass. Most of the rock on the moon's surface is primarily SiO2 quartz, so it is literally glass.
Yeah, so it's the silicate composition.
The silicate composition is SiO2, which is just, in this case, it's the crystal form of your window pane.
So that can cause a lot of problems. We've discussed that in the past, of course, the type of issues. And here you want to, you're thinking of the future with the Artemis project and then an extension after that, that there's probably going to be some double airlock on the moon where you go into the first chamber, and that's a decontamination chamber to get rid of the dust, get rid of your clothes. and then go into the main habitat part of the base on the
Right.
moon itself.
That or you have some type of docking system where you leave your suit outside.
Yeah, or that,
Yeah.
or some way to evacuate it. So you remember the Blue Ghost lander from so that landed was just a few weeks back from Firefly Aerospace, right?
Right.
So one of the things that was on board that was an experiment about how to get rid of the dust. Now, it was reported by the Apollo astronauts, Apollo 17, the last mission to the moon, human mission to the moon, that under the right sun angle, you could see the dust levitating off the surface of the moon.
That's a lot of static electricity.
Well, that's it. How cool is that, though?
Yeah.
Right? So it's static electricity that's doing that. It's like, you ever get a package from some place like Amazon or wherever, and you unwrap your gift and there's a little piece of plastic stuck to your finger and you can't shake it off because the electrostatic charge.
Yep.
So then you go up to somebody and say, how are you doing? And pat them on the back and hopefully transfer that piece of plastic to them. No, don't do that, but you know what I'm talking about. It's the same kind of thing, right? It sticks to everything because of that electrostatic charge. So this experiment that they ran on the lunar lander a couple of weeks back was to set up an electric field across the panels that you see there. And so on the left side is before the electric field was turned on. So you see the accumulation of dust on the panel. And on the right side is when they turn the electric static field on. And they have it in such a way, of the polarity-wise, that is the charge sign, that the dust is attracted to the side and actually migrated across the panel to the side. So the ideal here is that I can envision if it's on close, you could go to some type of, you can walk between two capacitor plates or something, some device where electric field is set up, and that dust then actually be attracted to the sides somehow, and then gets
A lot of it would be anyway.
and then get vacuumed out of the system, right?
Right.
So these are experiments that try to mitigate the buildup of dust.
Right.
And that's something that one of the things that we definitely have to pay attention to for future exploration of the surface of the moon itself. So we'll see how that plays out.
Yep.
Now, Robert,
Yeah.
do you plan to be here in 23 billion years?
No.
Well, then you're going to miss something fantastic. You're going to miss the potential explosion of two merging white dwarf stars that will collapse and form a supernova type 1a, a carbon detonation supernova. These two stars are about 160 light years away from us. And when they undergo this event, calculated to be in about 23 billion years from now, during the explosion, it'll be as bright as 200,000 Jupiters. It will have apparent magnitude in the visual of -16, apparent magnitude.
Apparent magnitude.
Apparent.
Holy cow.
Not
That's getting up
absolute.
close to the sun.
Yeah, the sun's like -26 or something,
Yeah.
right? So this is a lot
Holy cow.
dimmer. So it's as bright as 200,000 Jupiters.
Anything to keep from using the metric system. Sorry. sorry. I shouldn't say things like that.
Talk about bright in the night sky.
That is
Even
bright.
if it's a night sky, or it could be the day sky, depending on
Yeah,
when
that'll
the
be-
The problem is, of course, it's calculated given the orbital characteristics of the system, and that those orbital characteristics, by the way, is the panel that is on the right-hand side. It's gonna, and 23 billion years from now, that's long after like the Andromeda galaxy and our own galaxy, the Milky Way, has merged together.
Which means
long
this thing
after
will
the
be
sun
thrown
is
way
turned
out.
into a white dwarf.
Yeah.
The present location of this pair of stars is 160 light years, but what will it be in 23 billion years from now? It's gone around the Milky. Well, what's the Milky Way and Andromeda? That
Yeah.
you don't even know where.
Was it thrown out on a tidal tail? Was it shot into the supermassive black hole of one or the other?
It could be
You know,
anywhere.
could be anywhere.
So
So
yeah,
I don't know why
this,
they're.
This is a fun thing. This is also published in Nature Astronomy, by the way. So
Yeah, it's one of those neat things, but in the end, who knows?
well, I was going to say it's too bad it wouldn't go off like about 1 year from now or something.
Right?
And to be that bright, that would get everybody's attention.
Yep.
A lot of people would think the world's going to end, but it wouldn't. It's far enough away, it's not going to hurt us.
Right.
But boy, would it ever get people interested in astronomy, right?
Right? I mean, suddenly we don't the year without a day, without a night. I mean, yeah.
You know, in physics and astronomy, a lot of times well, not so much astronomy, but in physics in general and in science, we model things like a closed box system to keep it not so complicated.
Right.
And in astronomy, we quickly learn there's no way you can do that. If you just think about the Earth and the solar system, you always worry about things coming inbound, right? Somehow.
Right.
So, yeah.
I still remember in a class I took called Stellar Photospheres. One of the places we started was modeling the photosphere as it being in local hydrostatic equilibrium. And I, among a couple of others, raised our hand and goes, but that's not even remotely the case. And the professor just laughed and was like, yeah, but we got to start somewhere.
Well, that's the old thing. Assuming a cow's a sphere,
Right. You gotta
go from there.
The math is much easier with that sphere.
And then you can always come back, of course, and add complexity.
Right. And that's exactly what he was getting at.
Yeah. So you imagine from the point of view of fundamental physics. Mm-hmm. So you're in the quantum mechanics, right? Describe the performance of a monkey.
In terms of quantum mechanics?
Yeah. So
no, thank you.
Right? So you're going right down to the subatomic scales.
Yeah.
Right? But the complexity of a monkey is so great, there's no way you can go from there to the monkey.
Right.
It's just too much. So you got to start somewhere.
Right.
So maybe you look at the complexity of a monkey's arm. And that's too much.
Or maybe look at it as the thermodynamics of some Boltzmann statistics, you know?
Then you look at maybe a part of the fur of the monkey, right? A strand
Right.
of fur. So you just get down to simpler and simpler and simpler things that hope that you can solve that, or at least have a good understanding of it, right? That your models match reality as best as what you can, and then add the complexity and add the complexity and add the complexity.
And hopefully you keep mimicking, modeling what's really happening. And if you do, you eventually get a set of equations that say, here's a monkey.
You know, that's why understanding life and where it comes from, understanding biology is so difficult.
Right.
It's not an easy sort of process at all. In fact, historically, biologists are studying like macroscopic types of properties and characteristics.
Right.
Because there's no way to go from fundamental quantum mechanics subatomic level to build up to why, you know, a life form does a certain thing or whatever, right? I mean, it's so difficult. And as, you know, people always say, you don't know everything because you're a scientist, but you don't even know where life comes. How do you not even know where that life, because it's extremely complex, people, right?
Right. We're still building up to that complexity, you know?
Well, how many years in the past do you go before we didn't even know anything about DNA and RNA and that type of stuff, right?
Not terribly far.
So over time, we learn more and more and more, and eventually, hopefully, that nut will be cracked, that we will understand how we get from something that's not alive to something that is alive.
You got it.
And that's one of the major, I would say, the fundamental question in biology, at least for me, is how do you do that transition?
Right.
And clearly,
I agree.
And clearly, it's happened here on Earth. Mm-hmm. Whether it's happened anywhere else, who knows? Statistically, probably yes, but we have no proof of that, of course. But we know it happened at least once. So can we reproduce that? And people have tried. You know, they can make amino acids by putting different compounds.
They can even make complicated amino acids.
Yeah, and then you add electricity, you know, to simulate lightning in the early primordial Earth type of stuff.
You can get what's called a micelle, which is essentially a spherical distribution that has a membrane around it. So, you know, we can mimic certain of the aspects, but we're not to where we can combine them all yet.
Yeah, and I mean, we have a good understanding, for example, we think we do, of cosmology, the universe as a whole. And people say, oh, it's so complicated. How could you, and things are so far away. How could you possibly even understand even a minutiae of the cosmology of the universe around us? We can know about grand things, but when we get down to the levels like biology, as we mentioned, the systems are so complex.
Yep.
I mean, it's something to strive for, right? It's a target.
Right.
It's a goal.
You know, why would you give up?
And you can't just throw everything in the pot at once, because you're not going to make any progress at all. You've got to, you know, assume the cow is like a sphere and go from there, as the joke goes, right? That's what you got to do.
Yep.
But speaking about cosmology,
right?
I wanted to share with you some information that's come out lately about dark energy. In order to kind of appreciate what this is all about, we need to turn the clock backwards a little bit, go back in time, And think about the year 1998. And that year, there were two papers that were published and roughly within a few months of each other. The first one was by Adam Rees, the next one by Saul Perlmutter. And the two teams of astronomers were working on trying to measure initially the slowing down of the universe's expansion. And you might wonder, why would the universe's expansion rate be slowing down? First of all, that expansion was discovered by Edwin Hubble. He gets credit with it. And Father Lemaitre was also involved. So it's really Hubble Lemaitre, as we try to say nowadays, right? To be politically correct and to make sure people are properly credited. He discovered that roughly 100 years ago, that the universe was in a state of expansion.
Yeah, it has been 100 years,
Yeah,
hasn't
the
it?
1920s.
Yep.
So with that discovery, we went from assuming that the universe was completely static, that is neither expanding nor contracting. And that turns out to really have a profound effect on how you view gravity. Where gravity is an attractive force, it's very difficult to have a static universe.
Right. Because things would be pulling themselves together.
Yeah, and some people got around that and say it can be an infinite universe. That's how you get around with it. But it turns out that's not the case. That doesn't work either when you do the detailed mathematical calculations of that. So in Einstein's general theory of relativity, naturally a solution comes out that the universe is either in a state of expansion or one of contraction.
Right.
Not
It can't stand still.
It can't be static. So at the time, Einstein, you can't blame Einstein, he asked the astronomers, well, what is the status of the universe? And they would tell Einstein, well, you know, this is like before the 1920s, it's static, it's not expanding or contracting. So then Einstein went back to his field equations and said, you know, I have to introduce a term here that I don't want to do it.
Right.
It's messy. And that term will prevent the universe from expanding or contracting. It turns out, when people look at this in detail, it actually wouldn't work, but that's besides the point. Right? So in some sense, you can think of it as Einstein was fudging his equations.
And he called it his greatest blunder.
Yes, well, supposedly. George Gamow has reported that.
Okay.
But there's no report that Einstein said that directly.
Oh, I did not know that.
And I guess George Gamow was a kidder.
Yeah.
And we don't know exactly if he was fooling people or not when he mentioned that. So we don't really know.
Okay.
So, but let's say he did. We'll go with it, okay?
All right.
So, and the reason why they say Einstein said it was his greatest blunder is because there was no need for that. It doesn't fit into the theory naturally. It was
Right.
put in there
To make
as
it work.
to make it consistent with the observations of the time.
Right.
And so Einstein could have had enough faith in his equations, if I use that word in a science point of view, to say, you know, according to general relativity, I will predict that we will discover that the universe is either in a state of expansion or collapse.
Right.
In some sense, it could have been the greatest prediction ever made by humans.
Right. And in a way, it ended up being so because it was one of the confirmations of general relativity.
So since that time in the 1920s, the universe, we know, is in a state of expansion. But that expansion rate then would be dictated on what the universe contains. For example, the universe, as we know, contains matter. We're here, the sun's here, the planets are here, galaxies are here, et cetera, et cetera. And it also contains energy.
Which is matter.
Yes,
E equals mc squared.
Exactly. So because it contains matter and energy, then, that would want to cause the universe to slow down the expansion rate. It's like throwing a good analogy of this is throwing a rock in the air. Now, as soon as that rock immediately leaves your hand, it's moving the fastest upward that it possibly can move.
Right.
Any height above your hand, it's going to move at a slower speed. And the further it gets away from your hand, heading upwards, the slower and slower and slower it'll travel until eventually it'll come an instant in time where that rock suddenly stops moving upwards
And starts to
and
fall.
begins to fall downwards. So think of the expansion of the universe like throwing a rock upwards. Immediately from the expansion, so this would be the Big Bang, the universe is going the fastest, expanding outwards, and over time it's just slowing down and slowing down, slowing down because of the combined gravitational influence in the universe itself.
But there's a caveat to that. What if you have an engine on it?
Well, let's not get there yet.
Okay.
Okay.
Let's hold that one for a minute.
Let's hold
Okay.
that one. Now, you might wonder, well, how fast is the universe slowing down by? So what is the change in the expansion rate? So you can think of, like in science or math, we would call what is the time derivative of
Right.
the expansion rate. So if it's slowing down, how much is slowing down? And why that question is important, because the slowing down of the expansion rate is determined by the combined effect of all the matter and energy in the universe. And that is important because over the last several decades, especially in the 1970s moving forward, we discovered that there is matter in our universe that doesn't act like ordinary matter that you and I are made up of.
Right.
This type of matter, which we ultimately call dark matter, as far as we can tell, it doesn't emit light, it doesn't reflect light, it doesn't absorb light. We only know its existence because of its gravitational influence of surrounding things that we do know, normal things.
Yeah. And really, they're not, I can't think of any normal particle that does not interact with the electromagnetic force in some fashion.
The neutrino.
The neutrino, right.
Right? So the neutrino, so it would have to, if it has a charge, it's going to interact electromagnetically.
Right.
So it would be neutral in that sense. So, but neutrino interacts with the universe through the weak force, but because it has a small amount of mass, also gravity.
Right.
Right? You can't ignore that. So the thing is then, we wanted to understand what was this dark matter, how much is out there. Well, the dark matter would affect the changing of the expansion rate of the universe.
Absolutely.
In fact, our best estimates are there is 5 times more dark matter in our universe than ordinary matter. So it's not like the stuff we're made out of it is the majority. We're actually almost like the sprinkles on the cream of a coffee or something, right?
Right.
It's a very small minority. And because it's such a major contribution, the dark matter to our universe, it should have a great effect on the change of that expansion rate. So by measuring the change in the expansion rate,
we should be able to get how much dark matter is out
right,
there.
it gives us evidence
Yeah.
of that. So in the 1990s, when these two teams of astronomers eventually discovered this dark energy, which we'll mention here in a second what that's all about, what they were first doing was trying to measure the change in the expansion rate. In fact, we are so confident that the expansion rate would be slowing down, they actually called it the deceleration parameter.
Okay. Yeah.
So it wasn't a matter of whether the universe was slowing down. It was a matter of how fast is it slowing down,
right.
which ties directly, as we said, to the total amount of matter, both dark matter and ordinary matter, in our universe. So that's what they were trying to do. Now, to measure the expansion rate of the universe and how it slows down, one way to do it is to have an object called a standard candle, which we know its intrinsic brightness or luminosity is, like, think of a wattage of a light bulb.
Okay.
And we can use that to independently measure the distance to these objects, independent of the expansion rate of the universe.
Right.
So in the 1920s, Hubble showed us that the further away a galaxy is from us, the greater it's moving away, greater its recessional velocity. And we can measure that from looking at the spectrum of a galaxy and the displacement of the spectral lines from what it would be if the object was at rest relative to us. So the further away a galaxy is, the greater is its redshift, as we say. So the spectral lines are shifted to longer wavelengths. And it's due to the expansion of the space between us and that galaxy.
Right.
The more space between us and some distant galaxy, the faster that distant galaxy is being carried away from us due to the expansion of space itself. Now, you can measure distance by looking at the redshift of a galaxy, so long as you have the system calibrated.
Okay.
So there is a relationship between recessional velocity and distance. So there is a constant proportionality in that relationship. And as long as you know that value, then you can directly do that conversion. And that constant proportionality today we know of as the Hubble constant.
Okay.
Okay? Which is really a measurement of the expansion rate.
Right, again,
now,
of the
today,
locally.
locally.
Okay.
Okay? So you can go out and measure distances then to different galaxies, not directly, but by measuring their redshift, and then using the appropriate value of the Hubble constant, you can then calculate how far away that particular galaxy is.
So as we look further and further away, the Hubble constant actually shouldn't be a constant. It should be getting larger.
It would only be a constant if the expansion rate was a constant.
Right.
And because prior to 98, we thought that the expansion rate is slowing down with time, the Hubble constant would get smaller and smaller and smaller in value with time. So if you went back into the past, look at galaxies further away, so you're looking back into the past, then the Hubble constant would be a larger and larger and larger value.
Right.
Okay. So what they did in the 1990s is that they used a different object to calculate distance besides redshift, and these are these supernova type 1a, the same type that we mentioned in the previous slide. Okay, so they tie in here. What these supernova are the end state of a low mass star known as a white dwarf. And a white dwarf then is really the remaining core after a low mass star has burned helium into carbon and oxygen. That carbon core gets smaller and smaller and smaller till the density gets so great, the electrons, and here's a classical way of thinking about it, not a quantum mechanical way about it. It's like the electrons get jammed side by side and they resist going inside each other in some sense.
Right.
The Pauli exclusion principle,
Yeah.
as we learn in high school first, in chemistry class, I'm assuming, which just means you can't take two objects and kind of put them inside. They don't have the same quantum numbers, as we would say. This kind of
As a
stuff,
more
right?
advanced
As
level.
a more advanced level, thinking about it. But I like to think of it as marbles in a jar. If
Right.
you have an empty jar, glass jar, and you pour marbles in it, and you fill it up, and you could take another marble, put it on top, and it stays there. But then at some point, you're going to take that one marble and put it on. It doesn't matter where you put it, one marble will fall off. You just can't handle it anymore on
Right.
the pile. And you could jam it in by putting your hand on, if you had the strength, and force it into the pile, but then you might split the side of the glass container that's holding
Right. You'll
marbles.
either split the jar or you'll break marbles.
Right. And so these marbles are like electrons. They resist getting any further close together. So this object then, it's made up mainly of carbon, then halts getting smaller, halts the contraction.
Right.
So it counterbalances gravity. Now these things are extremely dense. You know, a core that's the size of 25% the size of the sun right now, would shrink down into a size about the Earth.
Right.
So the sun ultimately would turn into something about 1/100th its present size, which is the size of the Earth itself. And we call these objects white dwarf. And the material, because it's so dense, it's not like ordinary material. So we call it degenerate material. It has a different equation of state if we want to think more of advanced physics. So how we describe how the density and pressure changes with temperature and stuff, you have to use the appropriate equation for that state of material.
Right.
That's how it would be different, right?
And
Now,
okay.
what they discovered was that if you take a white dwarf and you add mass to it, and that could happen if it was near another star.
Right.
So most stars in our universe are not isolated like our sun. They're actually in binary star systems or in multiple star systems. And you could easily visualize, and it happens, we know, that you could have a white dwarf that's in orbit around another star that had a lower mass, ultimately. And that other lower mass star, because it takes longer to go through its life cycles, it eventually finished on the main sequence converting hydrogen and helium in the core. And one thing that happens is the core will shrink, will contract. It will heat up the surrounding hydrogen immediately surrounding the core. And then once it reaches about 10 million Kelvin, that hydrogen will fuse into helium in the shell burning around the core. And that actually causes the overall size of the star to get larger. It swells up and turns into an object that we call a red giant. And during this expansion of the size of the red giant, some of the material, if the star is close enough to the white dwarf, can be transferred on top of the white dwarf. So you can have mass transfer occurring in
Right.
these binary star systems. It's not unusual. Like I said,
not
it's happened
unusual.
many, many times. And what could happen is if you keep adding mass to the white dwarf, and this is something that Chandrasekhar calculated many decades ago, if you get to the point where the mass of the white dwarf reaches about 1.4 solar masses, called the Chandrasekhar mass limit, the electron pressure cannot stop gravity from collapsing the white dwarf. So the white dwarf essentially implodes rapidly, and the whole thing blows up as what we call a carbon detonation supernova, a type 1a.
Right.
Now, the interesting point of this from the point of view of cosmology and how it relates to dark energy is that because these white dwarfs, the progenitors are essentially the same beast, a white dwarf that just exceeded 1.4 solar masses, When they blow up, they can be calibrated. I like to think of it in an easy way or an analogy like sticks of dynamite. If you had 10 identical sticks of dynamite and you lit one off at a time and you measure their peak brightness, if they are truly identical, they should reach the same peak brightness.
Right.
Okay? So if you take that stick of dynamite and put it very far away, miles and miles and miles away, and then light it off, you could actually calculate the distance to that stick of dynamite based on the fact that you know its intrinsic brightness, its luminosity.
It really is.
And you know light falls off as 1 over the distance squared for uniformly radiating sources. So then you could use that information then to calculate how far away was the stick of dynamite moved so it has the faintness that it has now when it exploded.
Right.
Same as these type of objects. We can calibrate them. We know their luminosities. So then we can estimate then how far away they are. And we can compare then that distance to what we get when we use the redshift of the host galaxy. And the difference is the difference in that expansion rate, you see?
Okay. So that's how they did that.
And what they discovered in the late 90s was the supernovae were about 0.25 magnitudes dimmer than what they expected. And that means they were further away than what they should have been because they were brought closer because of the accelerated expansion of the universe. So they were about 25% dimmer than what they expected based on the redshift you calculate from the expansion rate of the universe. So what they discovered in 98, the profound thing that links to the dark energy, is that the universe is not slowing down.
It's
not
up.
decelerating, it's accelerating. It's an accelerated expansion.
Interesting.
Now, of course, you don't take that result lightly. So the teams will tell you they double-checked and quadruple-checked their results. But the nice, interesting thing is there was 2 independent teams of astronomers doing essentially the same thing at the time. And and they came to the same conclusion, both teams.
Right.
So that
which brings the question up, clearly they weren't doing the exact same method, but they came to the same conclusion. Were they in contact with each other at all?
They were in contact because they were presenting results at conferences and so on.
Okay.
And they weren't using the exact same supernovae samples.
Okay.
The other thing is people automatically, when this came out, it was so profound of a change. And I remember when this occurred, that you think immediately of a way to get around this result. The universe just became messy.
Yeah.
It just became way more complex. Because number one, what would cause the universe to accelerate? It's like an anti-gravity type of force that exists or permeates through all of space. What the heck is it?
Yeah.
And it's weak enough that you don't notice the effects locally. It's only over large cosmological distance scales that the effect accumulates that it becomes noticeable. But what is it? And what you turn to right away is say, our fundamental law of physics. Now, what is the most fundamental law of physics we have? Quantum field theory. So you go to the big boys, right, and big girls, and you bring out quantum field theory, and you calculate to try to see if there's any explanation for the dark energy. And they came up with 2 values.
Okay.
One of them is a nice value in terms of the complexity of the universe, and that value is the dark energy is 0. There isn't any, which is what we assumed was the correct answer. The other value, and it depends how you calculate it, okay, but a sort of an average result that I've seen being published 20 years ago, is that it's the current value of dark energy that we actually measure times 10 raised to the power of 120. It's 120 orders of magnitude stronger than what we actually measure. In fact, if our universe had that amount, that strength of dark energy, immediately when it formed, it would have just expanded so fast, nothing could form due to gravity.
Right.
No stars, no galaxies,
not even any protons or neutrons.
No us.
Yep.
The dark energy would be so strong that even if you think of the space between electrons and the nuclei of atoms, that amount of dark energy in that little space would be enough to rip those atoms apart. They would never form in the first place.
Right.
Clearly, that is not the universe we live in. Thankful for that. See?
Thankfully, I mean, we just wouldn't be here. So
yeah, so it's got to be 0, right?
No, not
That's the
necessarily.
only two possibilities. Remember, that universe, which is too extreme for our universe
Right.
to describe it. So it's got to be zero was the only other possibility, the only other solution to all of this. But then in 98, we discovered that is not the case. There is dark energy, just a weak amount of it compared to that one extreme value, but it's not zero.
Right.
So if it's not zero, and by the way, so there has to be an explanation. So people said, well, how can you make these supernovae dimmer? You only need 25% to make them dimmer, then you kind of explain away the dark energy. Maybe there's more dust sprinkled throughout the universe. Okay?
But that would absorb light.
Well, yeah, it would show up in the infrared. And in the late 1990s, we've had lots of infrared telescopes in space looking around. We don't see that dust. Well, how can you hide it in the infrared? You make gray dust. And gray dust is dust that is very large, so that it affects even the infrared light gets absorbed by that dust, you see?
Uh-huh.
So it becomes kind of neutral in some sense in terms of the absorption. You have the same amount of absorption overall, optical, and even into the infrared.
But that should be visible then in microwave or radio.
You should observe it, and there's no evidence at all. But here's the point, right, about that. Today, we have different techniques that have nothing to do with type 1a supernovae that can measure the expansion history of the universe. And all of those other techniques point to a finite value for dark energy. So we don't have to rely on the initial discovery. We have other ways of measuring dark energy, and they are all pointing to the same answer.
Okay.
They are all consistent.
So quantum dynamics field theory needs to get on the stick and figure out why it's not 10 to the 120.
Well, clearly we're missing something, and that's not surprising in the sense that we don't really know what go on in different locations of the universe. You know, what's going on at the center of black holes. We have mathematical singularities, all of these kind of things. You know, what about string theory? People hear about these exotic type of physics. String theory predicts that there should be these supersymmetric particles, yet the Large Hadron Collider hasn't found any evidence of them at all. So the simplest form of string theory is long gone away now. It's not correct, right? So there's a lot of work that needs to be done in fundamental physics. So anyone who's interested in math and physics, in terms of mathematical physics, there's lots of work for you to do.
Yes, indeed.
So to get on to what's going on here with the dark energy, we can then, since 98, look at, if you like, the chronology of the universe. So the Big Bang happened. Now, people ask, what happened before the Big Bang? What banged and why did it bang? The answer is, we don't know. Now, right away, there's all, you don't know about the Big Bang itself, then you don't know anything. No, we know a lot of stuff. It's like understanding where did life come from. It's extremely complex.
Right.
It's not easy.
And we might not know what banged and how it banged, but it's clear something happened.
Something happened. It's clear that the early universe was very dense and very hot. Okay, we can say that. Now, why do we say that? Because we can measure the leftover heat from the Big Bang. We measured that in 1964, the cosmic microwave background. So we know that that's out there. If the early state of the universe was not dense and hot, why would there be this leftover heat? You see, it shouldn't be there. So we have evidence of that. Now, and the other thing is, we have a mystery on our hands if there wasn't a dense, hot phase to the early universe. We know that stars form from hydrogen. Stars do not make hydrogen. Hydrogen gets transferred into helium, fused into helium. Helium into carbon and oxygen, and so on. And then we have supernova explosions that can produce all of the high heavy metals,
And
collisions of
collisions
neutron stars, magnetary interactions, all these things, right, that can populate all of the periodic table. But where did the first generation of stars come from? How did you form that hydrogen to begin with?
Right. And to be honest, I've never understood that. So.
And it turns out that you can produce those light elements, you can make them in the fire of the Big Bang in the first 3 minutes.
Okay.
There was enough energy around that you can make these elements. You can make the hydrogen, you can make the helium. In fact, not only that, given the expansion rate and the cooling down of the universe with time, you can calculate for how long was the oven on so that you were making this hydrogen and you're making the helium and trace amounts of lithium, beryllium, and boron, and it exactly matches the abundance that we measure around us today.
Okay.
So the predictions match observations. That's what you're looking for in science. Right. Okay? So they are consistent, but they're only consistent with a very dense and hot phase to the universe. So it's
Okay.
got to be there. That doesn't mean everything was crunched down to a single point at t equals 0.
Right.
Right.
In fact, that is empirically impossible.
Well, our known laws of physics completely break down.
Right. But that's more the point is the known laws of physics break down after a certain point, and that's why we can't say what banged and how it banged.
Which means that having a mystery like the dark energy is no surprise because there's a lot of stuff that we still need to figure out. So the Big Bang happened, the universe was created. It also went through this phase, which we don't have time to talk about today, of this expansion due to inflation. And then the expansion rate slowed down, went through a stage of deceleration. And it was only a few billion years ago that the energy density of dark energy started to dominate the universe over matter and radiation, that the expansion rate started to accelerate.
Okay.
So that is interesting. Now, where does that come from? Well, if you think of the equations, I'm not going to go in detail here.
I was about to say, you just had every eye that's watching this glaze.
I just wanted to show you that we can describe a lot of this physics mathematically, which is ultimately what you need to do in order to get somewhere. Look for a relationship between things. And what this is to say that you can think of the dark energy in terms of a substance with an equation of state. And we mentioned that already today, the equation of state. For example, the air we breathe, the ideal gas law, right? There's an equation of state, right?
There's an equation that describes how that
how
gas...
volume, pressure, and density and temperature are interrelated with each other and so on. And so the equation of state of dark energy, we try to put it in the simplest form, and it's equal to the pressure divided by the density. And we call that ratio W. Why not? Okay?
Okay.
Hey, it stands for Wayne. I'll take that.
Yeah.
And if the value is equal to -1, that is the cosmological constant. That is the fudge factor that Einstein introduced many, many, many decades ago to force the universe to be static when he applied his general theory of relativity.
So why isn't the universe static then?
Okay? So that is what he applied.
Okay.
That's what he stuck in there.
All right.
Now, the other thing is that this value could change with time. And if it does, it's not the cosmological constant.
Okay.
There could be a time dependence on it. And that's what you see in the very bottom, time evolution. So W then is made up of two things, a piece that doesn't change, a constant piece, plus a piece
Changing
that
piece.
does change.
Yeah. And a lot of stuff in
Yeah,
nature
and you
works
add it
that way.
together and you get the overall W,
Right.
which is a function of time. But all indications were that it was a constant. Now, if it was a constant, there are some profound implications for this. And one way to illustrate it in this slide is what we have on the y-axis. You think of just the energy density, and that energy density could be in the form of matter equals mc squared, could be in form of radiation, like the photons from the leftover heat of the Big Bang, the cosmic microwave background, and also in the form of dark energy. Now, on the x-axis, the bottom axis, that's just redshift, essentially. So when you look at high numbers like 4 on the left side, that means you're talking about the early part of the universe, very, very early part of the universe. If you go towards the right, once you get to 0, okay, that would be, for example, where we are today, essentially, okay? Now, the one thing to note here, there are two things that's being shown. There is radiation, that's the straight red line that you see there, okay? So it's a log-log plot.
Okay.
So it's a certain power law. Now, it tells you, if you look back to the left side very early, this is before redshift of 3000. There's a one dot that's labeled there in the top left corner of the plot. If you go back left of that, so you go back to an earlier time, the universe is dominated then by radiation. That's what we call the radiation-dominated era of the universe.
Mm-hmm.
The universe is expanding. The radiation then is filling up an ever larger volume of space. So you can think of a volume as the dimensions cubed, so
Right.
length cubed. Okay. As the universe expands and that radiation fills up an ever larger volume, it would fall off as 1 over that length cubed.
Okay.
But it's also being redshifted at the same time. So there's an extra length that you have to worry about it. So the radiation actually falls off as 1 over the length to the 4th power, not to the 3rd power.
Right. So bottom line, the amount of radiation energy per volume is decreasing as
Yeah,
we're
diluting away rapidly.
Right.
At this, the black curve that you see there, that initially it crosses over at that Z equals 3,000, or Z equals 3,000. And as you make your way to the right, notice it's labeled matter. So that's the density, energy density in matter. And notice that black line, that has a slope that's less steep than the one that illustrates the radiation, the red line. So the matter falls off too. It dilutes away as the universe expands, but the matter dilutes as 1 over the length cubed, just the volume effect.
Okay.
Okay. Now here's the interesting one. Look at the blue horizontal line. That represents dark energy. If W is really -1, you'd have this nice, beautiful horizontal line. So in the very early part of the universe, the energy density from dark energy is minute, is minuscule compared to the matter and radiation energy density. It is very, very, very small factor. But notice what happens. Because dark energy is a constant, if W is equal to -1, eventually what happens is the radiation density falls off, so they cross, okay? So all of a sudden the dark energy density is greater than that in radiation. And then eventually the matter drops below the dark energy. So then when you come to locally today, right, at 0 on that X scale on the bottom, on the X axis, that 0 marker, that vertical dotted line that you see there represents today, the thing that dominates then the energy density is dark energy.
Okay.
And that will become more dominant as we go into the future.
Right, because the other two are getting
dropping
diluted.
down dramatically where dark energy stays a constant. But here's something for you to ponder. Are you ready?
Ready.
If the dark energy is an absolute constant in terms of its density, like you see here, as the universe gets larger and larger, that means it contains more and more energy. So what happened to the conservation of energy?
Right. See, that's always been one of the things that bugs me is if this density is a constant, then somehow it's got to be coming from somewhere.
Now, according to people who look at general relativity, it doesn't violate any known laws in physics if cosmologically the conservation of energy does not hold true.
Okay.
Because we always think of conservation of energy and the energy got transferred into something else or left the system. It
Right.
can't leave the universe by definition. So
Right.
it is a closed box, you would think.
Okay. Okay.
Now, the thing that was released recently is a study that started 3 years ago using the 4-meter telescope at the Peak National Observatory. And I stuck in a slide of me visiting that telescope that I was using to do observations just a couple of years ago. That's the image on the left. But the result, the third-year result, is the one that you see on the right. This is from the DESI survey, stands for Dark Energy Spectroscopic Instrument Survey. What they're doing is looking at millions of galaxies, and this 3-year data includes 15 million galaxies, looking at their spectra. They get a detailed measurement of their distances. And what they are trying to map out is the dark energy effect of our universe, the accelerated expansion. Now, here's the interesting thing. The red dot that you see there, that would be for a value if the dark energy was an absolute constant, W equals -1.
Okay.
The green shaded area is the current 3-year results.
Oh, it's not constant at all.
And not constant at all. In fact, look at your WA value and your W0 values. They're not where they should be.
No.
W0 should be -1. WA, which is time evolution, should be 0. In other words, this is showing evidence for possible time evolution of dark energy.
Which closes a lot of the problems.
Well, what it does is it gets rid of all of those theoretical ideas that were predicated on there being an absolute constant dark energy of
Right.
W's -1. Now, caveat here, this is based on 30 years of data. There's 5 years in total for the survey, so 2 more years to go. This is not a 5 sigma detection. It's
Okay.
around 3 or so. And in physics, you know, like for particle physics, we don't claim a detection until we hit the 5 sigma mark.
Right.
So we have to wait and see, but it's extremely interesting. So if I was a theorist working in dark energy, I'd be coming up with all the models that explain the time evolution of
Of it.
because it may end up being the case. We have to wait and see.
Cool.
Okay, well, if you're interested in this or anything else, I mean, of course, turn to higher learning to get
Yep.
the nitty-gritty details of physics and quantum mechanics and astrophysics and mathematics, like we have here at
UND. Yeah.
both online and on campus.
Absolutely. So
Our next podcast then will be on April the 15th. We're going to have a very special guest.
Okay.
A mathematician will actually visit us from UND.
woot.
So we'll get into hopefully some interesting topics with him. We always leave a quote at the end.
Mm-hmm.
And today's quote is from William Herschel about the discovery of Uranus. And we mentioned Uranus
Yep.
at the beginning of the podcast. And it's interesting to think about the planet Uranus. This was actually the first planet discovered since ancient times.
Oh, right. It was.
So it's a real
yeah.
big deal. 'Cause
And it was
people-
also discovered by mathematics first.
Well, that was Neptune.
Oh, that was Neptune.
That was
Okay.
Neptune.
I thought
So
it was Uranus.
Uranus
Okay.
actually gets bright enough you can see with the eye, but it looks just like another star.
Right.
And even though several people put it on their star maps and stuff in the past, before William Herschel discovered it in 1781, they didn't know it was a planet. They
Right.
mistook it for a star, right?
Okay.
So it was almost, but anyways. So William Herschel then wrote in his logbook, and this is from March the 13th, 1781, from Bath, England, as they say. And I've been there, so I'm allowed to pronounce
Okay.
it that way. And in his observing book, he wrote, in the quadral near Zeta Tauri, either a nebulous star, or perhaps a comet. So William Herschel actually thought that Uranus was a comet in the beginning.
Okay.
A few days later, on March the 17th, he writes, I looked for the comet or nebulous star and found that it is a comet, for it has changed its place. And that's exactly what you expect also for a planet. It would have to move relative to the stars.
Yep.
And it was only later on, other people actually following up his observations, that they eventually realized it was actually a planet in orbit around our sun.
Okay.
Quite interesting to think about it.
Yeah.
Anyways, if you like this podcast, please give us a thumbs up. And thank you very much for watching.
Bye, everybody.